Podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to have fun with graphing. Love graphing. And let's see, they did an experiment where they put different weights on the spring.
And got different lengths.
Yeah, and so then the stretching changed. And so what they should have gotten was, since things are directly proportional per Hooke's law, they should have said, well, with zero weight, it had zero stretch,
Correct.
and it did something linear.
Correct.
Like this. And when we analyze Hooke's law, I'm just going to say it, I'm forgetting the negative sign here. That's bad practice, but I'm going to go, but since we measured the stretching in class to be positive as opposed to negative, which it actually is, I'm going to go ahead and just omit the negative sign.
All right.
Okay? That's bad math.
Especially how you just said, let's not do that.
Yeah, in that other podcast I said that that's poor practice, but I'm guessing that our students did not measure negative displacements.
Right. Absolutely correct.
So what you see here is that, well, that's the y, and the stretching is the x, and this kind of looks like something I once saw in an algebra class somewhere. So the slope is the spring constant k. And what you would determine is that if it were a shallower slope, this would be a spring that stretches easily.
Right.
And if it were a steeper slope, this would be a very rigid spring that doesn't stretch or compress very easily. But we have a nice direct or linear function to look at. The book, unfortunately for you, would like you to practice some things. And it would like you to rearrange some stuff. So what if we put the stretch on the y-axis and the force? By the way, force was due to the weight. So mg. Don't put mass. Mass is not a force. Mass is a measurement of inertia.
Right. There would be no force if we didn't have gravity.
Right. And so the restoring force, or the elastic force, was originally kx. But we have switched things around. We want to put x. We want to isolate x by itself and put force along the x-axis. So in order to do that, we got to divide everything by k. And so what we determine is that 1 over the spring constant times the elastic force is equal to x, or the stretch. And so our slope is now going to change to be 1 over k. Now I'm not going to give away the secret, so what we would like you to do is plot the data from page 403, question number 7.
All right. So, but they're not going to get the same graph.
Why?
Because it's not the same data that we're using here. So,
Yeah.
So, okay, so I'm giving a big hint, right?
I hope so.
Okay.
Let's give a bigger hint. What seems to be wrong with the data?
Oh, well, the first thing is that this is in centimeters instead of meters.
Right.
Okay, so, so you have to make that conversion.
Right. So make sure that you're paying attention to the units and to some other things. And there's a big hint here, at least in my opinion, about what's going on with our new slope, since we have rearranged the equation.
Right.
I'm going to go ahead and say ignore the rubber band experiment they'd like you to do. Rubber bands in the classroom just seem like a bad idea.
Right.
So
Like pushing someone in a chair, blindfolded.
that was a great idea.
Yeah, that was a great idea.
So go ahead and work that out and play with the equation. If you don't like to do this by hand, of course, Google Docs has some nice features to play with, or Microsoft Excel, so that you can adjust and play with the variables, what's x, what's y, and so on. So I believe that covers the basics. Signing off, this is Mr. White.
And Mr. Sadler.